Hello friends, here in this video we are going to see what is meant by dual cycle, and this is the fourth type of air standard cycle, that is after Carnot, Otto and diesel cycle. Here we have dual cycle. Now I'll write down that dual cycle, it is also called as limited pressure cycle, or it is also called as mixed cycle. Limited pressure cycle or mixed cycle. Now why it is called as limited pressure cycle? Because in this cycle here, in this cycle, the heat addition process takes place both at constant volume and constant pressure. So since the heat addition process is made up of constant volume as well as constant pressure, that is why it is also called as limited pressure cycle or mixed cycle, because of both the heat addition process here. Now this cycle is used for heavy duty diesel engines. And why it is used for heavy duty diesel engines is that here the heat addition process is extended, that is the time available for the fuel to burn with air is increased, and since we are increasing the amount of fuel, then we can say that it can be used for heavy duty diesel engines. Next, here I write down that the processes which take place in dual cycle are, now the first process is process 1 to 2. It is called as reversible adiabatic, which is isentropic compression. Then process 2 to 3, which is called as constant volume heat addition. Next we have process 3 to 4 as constant pressure heat addition. Here as we see, there are two heat addition processes, first at constant volume, second at constant pressure. Process 4 to 5, that is reversible adiabatic, also called as isentropic expansion. Next, process 5 to 1, it is constant volume heat rejection. Now, so these are the 5 processes which take place in dual cycle. And here I'll explain these processes on PV and TS diagram. So it is PV and TS diagram for dual cycle. PV is the pressure volume, TS is temperature entropy, and that diagram is basically a graph. For PV, it is a graph between pressure and volume. For TS, it is a graph between temperature and entropy denoted by S, which is the entropy. Now, I'll explain the process one by one. Since first is reversible adiabatic, that is isentropic compression. Here process 1 to 2, it indicates reversible isentropic compression, and as we can see here, at point number 1 the volume is V1, at point number 2 the volume is V2. So volume has reduced from V1 to V2, pressure has increased, and this process is called as isentropic compression. Next, the second process is constant volume heat addition, process 2 to 3. So heat will be added at constant pressure. First, it is constant volume, so heat is added at constant volume first. So 2 to 3 is constant volume heat addition, that is, once the heat is added, pressure will go on increasing and volume remains constant. So V2 is equal to V3. Then here we have another heat addition, which is process 3 to 4, constant pressure heat addition. So in this case the heat would be added at constant pressure. So this is point number 4. Process 3 to 4 is constant pressure heat addition. Here I'll mark it as pressure at point 3 is equal to pressure at point 4. Next, after the heat addition process at constant pressure, we have process 4 to 5, reversible adiabatic, that is isentropic expansion. So now, as it was for compression, the expansion process will also follow a curve which is isentropic process. So 4 to 5 is isentropic expansion. As we can see here, the volume at point 4, it was less, and the volume at point number 5, V5, that is equal to V1. So volume at point 5 is greater as compared to point 4. It means during expansion the volume increases and there is a drop in pressure. So here as we see, the pressure has dropped from P4 to P5. So expansion has taken place. Next, process 5 to 1 is constant volume heat rejection. So here heat will be rejected at constant volume, that is from 5 to 1. V1 is equal to V5. When the heat is rejected, pressure drops. So here I have shown the dual cycle on PV diagram. Now explaining the same processes on TS diagram. Process 1 was isentropic compression. So on TS diagram, isentropic compression where entropy remains constant, it can be shown with the help of a vertical line, state 1 and 2, and now I can denote here that S1 is equal to S2, entropy remains constant. So now process 1 to 2 is isentropic compression, process 2 to 3 was constant volume heat addition. Now constant volume lines are more inclined, that is, here I'll denote this line as a constant volume line. So heat is added at constant volume from 2 to 3. So here the heat would be added at constant volume 2 to 3. Now after constant volume heat addition, next is constant pressure heat addition from 3 to 4. So from 3 to 4 it would be constant pressure. Now constant pressure lines are less inclined compared to the constant volume lines. So this is a constant pressure line, and the next process 3 to 4 will follow this line, that is having constant pressure from 3 to 4. Constant pressure heat addition, temperature increases from zero point 0.3 to 0.4. Then again we have isentropic expansion. Now there will be isentropic expansion from 0.4 to 0.5, keeping the entropy constant. S4 is equal to S5. Then process 5 to 1 is constant volume heat rejection. So again there will be a constant volume line, and this should be of diverging nature, that is both the constant volume lines, they should not be parallel but they should be of diverging nature. That is the nature of constant volume lines on TS diagram. So from 5 to 1 there will be heat rejection, that is here is a heat rejection process where temperature drops from 0.5 to 0.1. So now I have shown on PV and TS diagram the dual cycle. I'll mark that from 1 to 2 here it is a compression process, so there will be work done in compression. Next 2 to 3 is heat addition at constant volume. So heat is added into the system. I'll denote it as QA1, that is the first heat addition. Next, after constant volume heat addition there is constant pressure heat addition. So I'll denote it as QA2, that is the second heat addition process. Then from 4 to 5 there will be expansion, that is we are getting work output from the engine, W suffix E. After that, once the work has been produced there will be heat rejection from 5 to 1, so that will be Q suffix R. Similarly, I'll show all the values here. 1 to 2 is work done in compression, so W suffix C. 2 to 3 is heat addition at constant volume, so it will be QA1. Next, after that 3 to 4 is heat addition at constant pressure, so here we have QA2, heat addition at constant pressure. Then 4 to 5 is isentropic expansion, so we are getting the work output, W suffix E. And then 5 to 1 is constant volume heat rejection, so here heat has been rejected from 5 to 1. Now after showing all the terms here, next I will be explaining this cycle in such a way that first of all at point 1 air enters the cylinder, or air is completely filled inside the cylinder. That is at point number 1. Next, when the air has been filled, after that compression of air takes place. So from point 1 to point 2, compression of air takes place, and it is reversible adiabatic compression, and reversible adiabatic compression means it is nothing but isentropic compression. Then I can write down that during compression process, the next point, during compression process there is decrease in volume with corresponding increase in pressure, keeping the entropy constant. So here, as we see in the diagram, that during the compression process volume decreases from V1 to V2, but pressure increases from P1 to P2. As we can see here, the pressure at point number 1 is less and at point 2 the pressure is more. So pressure has increased from P1 to P2, but volume has decreased from V1 to V2 and entropy remains constant. S1 is equal to S2 during process 1 to 2. Next, for 2 to 3, I'll write down at point 3, at point 2 first of all, heat addition, that is fuel addition, starts and it is added at constant volume up to point 3. During process 2 to 3, volume is constant, but pressure and temperature increases. So as we can see in the diagram, during process 2 to 3 the volume is constant, V2 is equal to V3, but pressure increases, that is P2, and here we have P3. P3 is greater than P2, so pressure increases and even the temperature increases. As we can see from the TS diagram, the temperature at point 3 is greater than the temperature at point 2. So temperature increases, pressure increases, keeping the volume constant. That is process 2 to 3. Next, after process 2 to 3, here we have constant pressure heat addition, which is the second heat addition. So I'll say that now at point 3, heat addition starts at constant pressure up to point 4. So heat addition starts at constant pressure, then during process 3 to 4, pressure is constant, but here pressure is constant, but we can see that from 3 to 4 the volume increases and even the temperature increases. So but volume and temperature increases. So now here I have written that during process 3 to 4 pressure is constant but volume and temperature increases. So we can see in the diagram that 3 to 4 pressure is constant, P3 is equal to P4, but volume has increased from V3 to V4 and even the temperature has increased from T3 to T4. Next, after that, the expansion process 4 to 5. So here I'll write down that once the heat addition process has been completed, there is isentropic expansion of air and expansion takes place from point 4 to 5, and I can write down, and during the expansion process, here entropy remains constant, but there is a drop in pressure and temperature of air. So here we can say that during the process 4 to 5, entropy is constant, S4 is equal to S5, but pressure has dropped from 4 to 5 and even the temperature has dropped from 4 to 5. Next, after expansion, heat rejection starts from point 0.5 and heat is rejected at constant volume from point 0.5 to point 0.1, and I can say that during this process both temperature and pressure decreases. So here, as we see in the diagram, for process 5 to 1 it is at constant volume process, V1 is equal to V5. Here the pressure drops from 5 to 1, and in TS diagram the temperature drops from 5 to 1. So there is drop in pressure, drop in temperature, but here volume remains constant. So here I have explained the working of dual cycle. Next, I'll write down, therefore, efficiency of dual cycle can be calculated by using the following concept. Now we can calculate the efficiency of dual cycle by using this concept. The first thing is heat added at constant volume, that is QA1 is equal to, it is constant volume, so CV, and the heat is added from 0.2 to 3 at constant volume, so it is T3 minus T2, so CV T3 minus T2, and here we are assuming the mass as 1 kg. So we are writing only CV because mass is 1, so the coefficient is 1 here, no need to write that. Now similarly, heat added at constant pressure, that is QA2, will be equal to, heat is added at constant pressure, so Cp. Now heat is added at constant pressure from point 3 to 4, so it will be T4 minus T3. T4 minus T3, again the mass is 1 here. Next, therefore we can say that total heat added will be equal to QA1 plus QA2, and that will be CV T3 minus T2 plus CP T3, it will be T4 minus T3, it was T4 minus T3, so T4 minus T3. Next, I'll say that therefore work done or work output which we are getting, work done will be equal to, it will be heat added, that is the total heat added minus the heat rejected. So here work done, it can be total heat added, which is QA1 plus QA2, minus heat rejected, and heat is rejected from process 5 to 1, so it will be, and it is at constant volume, so CV T5 minus T1. So this much is the net work which we are getting. And finally efficiency, it will be given by, that is the efficiency of dual cycle will be work done upon heat supplied, and heat supplied is nothing but the total heat added. I'll denote it as QA. So we can put work done in the numerator, then total heat added in the denominator, and from that we are going to get the efficiency of dual cycle. So in this video we have seen what is meant by dual cycle, its processes, PV and TS diagram along with its efficiency, and how to calculate that.